Welcome to Online Precalculus. Today, we will cover section P4, Polynomials. The objective for this section are to understand the vocabulary of polynomials, add and subtract and multiply polynomials. We can use the FOIL method to help us with polynomial multiplication, and also to understand how special products can help us multiply polynomials more efficiently, and also to perform operations with polynomials in several variables. So first, how do we define polynomials? So here's a statement: more education results in higher income. So we have two mathematical models, one for M, one for W, one for M, and one for men, one for women. And what these expressions show us is that it describes the annual income for men and women that have completed X years of education. These algebraic expressions are examples of polynomials. So what exactly is a polynomial? It is a single term or the sum of two or more terms containing variables with whole number exponents. Okay, so that's important. That means no fractional exponents, no negative exponents inside a polynomial. The polynomials above, right, each one of these have four terms. 1, 2, 3, 4. Equations containing polynomials are used in such diverse areas as science, business, medicine, psychology, sociology, all different applications for polynomials, especially when we're trying to model data. Okay, so we're going to start with the basics of how polynomials work. So let's consider this first polynomial, 7x to the third minus 9x squared plus 13x minus 6. And we can express that as the sum of the four different terms, right? We can just change the subtraction to adding a negative number, okay? So it's customary to write the terms in order of descending powers of the variable, okay? That is called the standard form of a polynomial. Some polynomials have only one variable, and each term of polynomial in x is of the form ax to the nth power. As long as the coefficient, that a, is not equal to 0, the degree of the polynomial is the largest exponent, ax to the n power. So for example, the degree of my polynomial in this example is third, because that is the biggest exponent. Okay, and so that's what this definition says. If a is not equal to 0, the degree of ax to the n power is n. The degree of a non-zero constant is 0, and the constant 0 has no defined degree. It's undefined. So here's an example of a polynomial and the degree of each of its four terms. So the first term has a degree of 4 because it has the exponent to the fourth power. Third degree, first degree, 0 degree. It has no variable. Or we could think of it as 5x to the 0 power. All right, x to the 0 power would turn into 1. Notice that the exponent on x for the term 2x is a 1, and the negative 5 is said to be 0. So let's talk about a little bit about some more vocabulary here and something called being simplified. Polynomial is simplified when it contains no grouping symbols, no parentheses, and no like terms. A simplified polynomial that is exactly one term is called a monomial. Binomial has two terms. Trinomial is 3 terms. If it's 4 or more, we don't give it a real special name. We just say polynomial of 4 terms, 5 terms, 6 terms, 7 terms. The degree of the polynomial is, like we said before, the greatest degree of all the terms of the polynomial. So while this term has a degree 2 and this term has a degree 1, we would say that that is a binomial of degree 2 because that is the biggest degree in the entire polynomial. The degree of the other term is less than 2, right? And here, the degree of this polynomial would be 5 because that is the largest exponent. And up until now, we've used x to represent the variable, but we don't have to. Any letter can be used. So the first one, 7x to the fifth minus 3x to the third plus 8, is a polynomial in x of degree 5, 3 terms, so that means it's a trinomial. Whereas the next one is a polynomial in y. So again, we don't have to always have x as a variable. Typically we will, right? That's the most common, right? Input, x for input, y for output. But we don't have to have our polynomial be defined in x, right? It can be defined in x, defined in y, and defined in z. The z polynomial is degree 7, and there are 2 terms. It's okay to have a irrational coefficient. It's just not okay to have an irrational exponent, right? The exponents all must be whole numbers. I'll tie all this together with a formal definition of a polynomial in one variable. When we talk about this definition, the coefficients of the terms are represented by a sub n minus 1, a sub n minus 2, and so on. The small letters to the lower right of each a are called subscripts and are not exponents. That is a very common mistake. Okay, they are just used to distinguish one constant from another, right? When you don't know what the number is actually going to be. So when we look at the definition of a polynomial, we see that the subscript and the exponent match. The subscript and the exponent match. And the only reason for that is to say this coefficient goes with this term. This coefficient goes with this term, and so on and so forth. It's just to distinguish that they could be different. They don't have to be different, but they could be different. And it just shows you which term each coefficient goes with. And we start with some variable x to the nth power. We start with some number n, and we go down by 1, then down by 2, then down by 3. The ellipses in the middle mean we keep going down, down, down until we get to x to the first and x to the 0 power, which is just the constant term. When all these numbers are real numbers and a to the n, a sub n, is not equal to 0, then, and of course the n is a non-negative integer, the polynomial is of degree n. We're just saying that that's the biggest exponent, that's the degree of this coefficient, or that's the degree of this polynomial, and that number in the front, this number, a sub n, is called the leading coefficient, and this number is called the constant term. Okay, those are important. All these are important words to remember, but probably the ones that we are going to use the most with polynomials are leading coefficient and constant term, especially when it comes to graphing these expressions. So leading coefficient, exactly what it sounds like, the one that comes first. Constant term, the one without a variable. So what can we do with polynomials now that we know how they are described and some of the vocabulary that goes with polynomials? What can we do? Well, first we're going to add and subtract. And very simple to add and subtract polynomials. They're just combined by adding and subtracting the like terms. For example, 2 monomials, both with x to the third power, you can just use the distributive property and put the coefficients together. And usually we omit this step and we just say that we can add the 2 coefficients together. Okay? So that's what we're going to do here. Right? So when we look at this expression and we have these different polynomials, what we can do, and we'll take the first one very slowly here, and we'll talk about exactly how we're allowed to do this, is we first use the commutative property that says we're allowed to add things together in any order that we want. So I'm going to go negative x to the third plus 13x to the third plus 7x squared plus 2x squared minus 5x minus 8x plus 3 minus 6. Then I could group both of these because they're both x to the third power. I could group both of the 9 and the 13 together, factor out the x to the third, and add the negative 9 and 13. Right? I'm going to skip over that step, and we're just going to combine the like terms to give me a 4, right? 4x to the third plus 9x squared. And then I could put plus a negative 13 so I can keep a polynomial always separated by addition, but I'm going to skip that step as well and just write minus 13x minus 3. Okay, so if I was looking at this polynomial, it would be a third degree, and it would have 4 terms. And then for part B down here, what I really want to do when I have subtraction is get rid of the subtraction and change the signs of each coefficient. So I would rewrite this without rearranging it. Plus 9x minus 6. I would change this to a plus, or actually I would just change this to a plus and change all the signs inside. So the 2 is a plus, it would change to a minus 2x to the third. The negative 6 would change to a positive 6x squared, positive 3x minus 9. I distribute the negative to all these things and drop the parentheses. Drop the parentheses, change the sign of each term. Okay? Keeps you from making a mistake. And now you combine the like terms. So when we do that, we get the 7 minus 2. So that's 5x to the third, negative 8x squared, plus 6x squared gives me minus 2x squared, plus 9 plus 3, that's 12, and a minus 6 and a minus 9 to give me a minus 15. Again, this is a third degree polynomial of 4 terms. Okay. Let's try the checkpoint questions. We'll do the same thing again. Okay, I'm going to go a little faster through these this time. Okay, so for part A, I'm just going to add these as I go because I have a addition. Right, so it's just negative 17 plus 16. So that's minus x to the third plus 4 minus 3. So that's plus x squared, right? Only one left over, and I don't need to write the 1 in the front. Minus 11 plus 3. That's going to be a negative 8x minus 20. For part B, however, before I get into combining it, I'm going to drop the parentheses and distribute the negative sign. So minus and minus becomes a plus 7x to the third minus 2x squared plus 5x minus 9. Okay, so then I put, whoops, that was the third power, right? 13x to the third. Then I put the x to the third powers together, and I get a 20x to the third. I got a minus 9 and a minus 2. That's 11x squared. Minus 7 plus 5 gives me minus 2x and a minus 8. Okay, and again, we have a third degree polynomial of 4 terms. So addition and subtraction, pretty straightforward. Okay, let's get into multiplication now. So the product of two monomials is obtained by using the properties of exponents, like we did in the previous section. So that means we're going to multiply the numbers, and because they have the same base, we're going to add the exponents together. Furthermore, we're going to use the distributive property if we multiply a monomial in the front, the 3x to the fourth, by something that is not a monomial, which means it has addition or subtraction signs, separated by addition. So we are going to distribute it across all the terms, remembering to add the exponents when we have the same base for each term. Okay? So we get 6x to the 7, negative 21x to the 5th, and 9x to the 4th when we distribute the 3x to the 4th to that trinomial. When you have two polynomials and neither is a monomial, one way to do this is to distribute the 2x and then the 3 and then combine the result. So that means we're going to distribute the 2x across, then we're going to distribute the 3 across, and then we're going to just combine all of the like terms. And that is a method that works no matter how big or small the two polynomials are. In this case, we have a binomial times a trinomial, and go figure, when we do this, we're going to have 6 terms that we have to combine at the end. Works for trinomial times a trinomial, then you'd have 9 terms at the end to combine. So again, our rule here is multiplying polynomials when neither is a monomial. Each term of one polynomial gets multiplied to the other polynomial, and then you combine the like terms. So let's actually do this problem with the 2x and the 3. Let me rewrite this so I have some room. X squared plus 4x plus 5. Okay, so I'm going to start by multiplying the 2x across each of the 3 terms. So that becomes 2x, x to the first times x squared is x to the third. Then 8x squared, then 10x. Now we do the 3. So that's 3x squared plus 12x, and finally my constant term is 15. There's no more x to the thirds, so there's nothing for that term to combine with. However, we do have an 8 and a 3 for x squared, so that gives me 11x squared, 22x with the 10 and the 12, and then the 15 is nothing to combine with. And again, look at that, we get a third degree polynomial of 4 terms. But when we multiplied the 2 by the 3, 1, 2, 3, 4, 5, 6 terms. Let's try our checkpoint. And I'll leave the room up top so I don't have to write this again. Okay, so we start with these two, which gives me 15x to the third minus 25x squared plus 20x minus 6x squared plus 10x minus 8. Okay, combine. Nothing to combine the x to the third with. 25 minus a 6, it's minus 31. 20 and a 10 is a 30, and a minus 8 at the end. And again, no constant term to combine with either. Okay, so another method of multiplying two binomials together is to use something called the FOIL method. Okay, so frequently we want to find the product of two binomials. We could always distribute, right? So you could always do the 3x to both and the 2 to both, which is what is being shown on the right side over there. Then we combine the like terms. The other method we can use is something called the FOIL method, which stands for first, outside, inside, last. And it's just a way to remember to multiply the first, outside, and look, I just distributed the 3. Inside, last. And look, I just distributed the 2. So it's still doing the same thing. It's just an easy mnemonic device that we could use to help us remember to hit all of the terms inside two binomials. Now, this doesn't work on this problem, on the previous problem, because it's not two binomials. There's this middle term right here, okay? So this works when you're multiplying a binomial times a binomial. And in general, when we do this, it's always going to be ax times cx, ax times d, the outside, b times cx, b times d. First, outside, inside, last. Okay, so instead of distributing this, let's use, let me rewrite this, 5x minus 3. Let me use the FOIL method. So first would be 15x squared. Outside, right, these two on the outside, would be 9x. These two are on the inside. So that is now 20x, and the last would be minus 12. Okay, and when we look, we just have to combine the two like terms. So we get 15x squared plus 29x minus 12. Right? When we multiply these two binomials together using the FOIL method. Now, do you have to use the FOIL method? No, you could just distribute one to the other. Same idea. In fact, with two binomials, it's actually the same steps, okay? But it's just a helpful way to remember to do this. And I think I made a mistake. I did. Look at that. That's a negative. So this isn't 29. I apologize. That is an 11x. Okay. Always check your signs. Check your signs. All right, let's try that again. Hopefully I'll get it right this time. All right, so we go. 7 times 4, 28x squared. 7x minus 3, negative 21x. Minus 20x. Negative times a negative on my last term is a positive 15. Combine the middle terms, give me 28x squared minus 41x plus 15. And I don't have that answer, but it looks right. Okay, so let's talk a little bit about some special products. Okay, these are the products that occur so frequently, it's convenient to try to memorize the pattern so that way when I see them, I don't have to think about it too much and I can just multiply these together. So the first special product is the sum and difference of two terms. So if you notice, you have the same term here, the same term here. That's what that means. The only difference is one is a plus and one is a minus, and they're binomials. 2x, 2x, 3, and 3. One's a plus, one's a minus. That will always result in the first term squared minus the second term squared. Okay? So these are just shortcuts, things that we can use to help us be faster, more efficient. Squaring a binomial, either with a sum or a difference. Okay? It's always going to be a squared plus or minus, depending on which one, 2ab plus b squared, right? No matter what the two terms are, when you're squaring a binomial, the technique can always be the same, right? So if we look at the first one right here, we would just take y squared plus 2 times y times 5 plus 5 squared as a shortcut. You could, of course, just multiply it out twice, and look, there's my y squared, there's one y times 5, there's another y times 5, and there's my 5 squared. Okay, so this does work either way. Remember, we're just trying to be more efficient. Now, the one you might want to try to remember is cubing a binomial. So when we cube a binomial, if you have any experience with the binomial theorem or Pascal's triangle, this might be a little familiar, but the coefficients go 1, 3, 3, 1. Right? There's a 1 in front of the a, a 1 in front of the b. Right? And the exponents start, a starts at the third power, second power, first power, then nothing, whereas b goes backwards, nothing, first power, second power, third power. It's convenient to try to remember this, or to use the binomial theorem, Pascal's triangle, to help you expand binomials quickly. For the sum, they're all pluses, nice and easy. For the difference, it goes plus, minus, plus, minus. They just alternate as you go. Okay? And again, these are just ways that we can multiply things together faster, right? And if we can recognize them, then it can help us be that much more efficient. So now let's shift a little bit and talk about polynomials in two variables, x and y, right? So it contains the sum of one or more monomials in the form a to the a, x to the n, y to the m. That constant a is always the coefficient, right? That's just the number in the front. And the exponents represent whole numbers. Still the same idea with a polynomial with two variables. We're still not going to have any fractional exponents. We're not going to have any negative exponents. But the degree of each monomial is the sum of the two exponents. So for example, the degree of this first term would be 5, this term 6, 2, 2, 0. Okay? Which would make the degree of this polynomial 6, because that's the biggest. Okay? So it's the highest degree of all its terms, except the exponents get added together. Okay? And again, if you have like terms, you're going to put those together as well. So if we have xy squared and an xy squared, we are going to add them together just as we would with a single variable term. So now let's multiply some polynomials with two variables. And we can start with this one. Let's FOIL it. So we will go first, which is 3x squared, outside, minus 5. And I usually try to write, when I have two variables, I try to write them in alphabetical order. So I got x and y here, so I'm going to write 5xy. 5yx is still okay, but it is better form to try to do it in alphabetical order. Or by degree, but in alphabetical order. Okay. So 4 times 3 gives me 12 xy, right? There's one x and one y. And for the last term, we have a minus 20 y squared. And notice that the two xy's are like terms. So we can put those together to give me 7xy minus 20y squared. Let's try one of our special techniques here, remembering that a plus b squared is a squared plus 2ab plus b squared. Okay, so if I use that technique here with this expression, I don't have to worry too much about writing it over again and foiling it together. I can just say 5x, the first term squared, plus 2 times the first thing times the second thing plus the second thing squared. And I just wanted to write this out to see every step. You can do this as you go to give you 25x squared plus 30xy plus 9y squared. Don't forget to square both terms. Okay. Let's try our checkpoints and do both of these again. So we'll FOIL the first one. We get 21x squared minus 7xy minus 18xy, and then a minus, so that's plus 6y squared, to give me 21x squared. 18 and 7 gives me a minus 25xy plus a 6y squared. That's part A. For part B, I'm going to use my special technique. I'm not going to write the formula again this time. So my special technique becomes a squared, so that's 4x squared, plus 2 times 4xy, which is 16xy plus 16y squared. And now I don't have to combine anything if I use that technique. Okay? So that would be my solution. Sometimes special products can be used to find the products of trinomials, as in our next example. Okay, so look at this very carefully. Right? If we wanted to, we could go 1, 2, 3, 4, 5, 6, 7, 8, 9, distributing all of these terms to all of the other terms, and then combine them. Okay. But if you recognize something, then it's a little bit easier. If you recognize that all of these numbers are the same, and the only difference happens there, we can use one of our special techniques. We can use this technique, that a plus b times a minus b is a squared minus b squared. But what's the a and what's the b? Well, look carefully. These two are the same. These two are opposite. So the a in this case is 7x plus 5, whereas the b is 4y. All right, so let's try this out. So what we're saying is that we now can have this our setup to be 7x plus 5 squared minus 4y squared. Now we use our special product or special technique there for the sum of a binomial squared. So that would be 49x squared. So that's 2 times 7 times 5. So that's 70x plus 25. Don't forget, square the inside here first, which means that it's 4y squared, which is 16y squared, and then the minus. So it's minus 16y squared. Way easier than having 9 terms that we have to find the ones that have like terms, and some are going to cancel, and then wind up with this second degree to, both a second degree polynomial with 4 terms. Same idea here, okay? In fact, because it's a sum, you could call these two a and this b, or this a and these two b. I would argue that it's nice to leave the 1 by itself because that's easy to multiply, okay? So remember to square, which we just did in the previous problem anyway, but I'll write it down again, a squared plus 2ab plus b squared, right? Our a is going to be this, so this is going to be 3x plus y squared plus 2 times 3x plus y times 1 plus 1 squared. Okay. So now we really don't have to do too much here. We do have to square this first term, and we can use the same technique again to get 9x squared plus 6xy plus y squared plus 6x. As I distribute these two, the 1, boom, right? It just multiplies by 1, just goes away. So that's plus 6x plus 2y, and then 1 squared is 1. So again, we could have set this up as 3x plus y plus 1 squared, multiply that twice, and got 9 terms, and then added them together. this, we got a polynomial with second degree polynomial with 6 terms, but still easier than the other technique. Let's do these one more time with our checkpoint and then make sure we understand how it works. 1 plus 1 minus. So we can say that this is going to be 3x plus 2 squared minus 5y squared. Right, this is part A. 3x plus 2 squared gives me 9x squared plus 12x plus 4 minus 25y squared. Okay. And for part B, we have 2x plus y. No real benefit to doing it like this, but I'm used to it, right? So I'm going to call this A and I'm going to call this B. Plus 2 times 2x plus y times 3 plus 3 squared. 2x plus y squared gives me 4x squared plus 4xy plus y squared. Distribute the 2. 2 and the 3 should multiply together first. That's 6. And then the 6 times the 2 gives me 12x plus 6y plus 9. Okay. And again, I just use the commutative property to multiply these two first and then distribute the 6 across. Okay. So that was section P.4 Polynomials.